Alright, so introduction to derivatives. A lot of just kind of talking in this one, but pay attention here. Basically, what is the derivative? The derivative, common sense definition, is just the slope of the tangent line to a curve at some point. So down here I got a little drawing of it. The derivative is just going to be the slope, or it could be a function to find the slope. It could be an equation that gets you the slope of the tangent line to a curve at any point. And just like in limits, we have multiple ways we can evaluate these. We do the numerical approach. Here, that's just constructing a table and finding the slope between 2 points and finding the slope between several points, actually. So you could do like 1 and 3, and they don't have 0 here, but you could do like 0 and 2, and you could kind of average those points, and you could find out what is the slope right at like 1.5. Some processes there you could do. There's a graphical approach where you just kind of look at the graph and you could say, oh, you know what that tangent line looks like? It's a slope of 1/2 or whatever it is. And the way that we're going to focus on here is the analytical approach. These two are still valid ways, and you'll see some questions where you have to do this, but most of the time you're going to be doing the analytical approach. So let's talk about that. And so here's a classic example. How did they get to here? Well, I'm going to show you how they found that the derivative of x squared is actually 2x. And so what this means is now you have an equation that you could plug in any x value in. So say you plugged in a 1. That means on this graph, this x squared graph, when x is 1, you could find the derivative or the slope at 1, and be 1 times 2 is 2. That means the slope at 1 is 2. And you could do the same thing for any other point. You could do the same thing for 3 squared. So that is at the point 3, 9. On this graph, the slope would be 2 times 3, which is 6. And so that's the beauty of the derivative function, is that it gives us the slope at any point on the graph. Okay, so one of the things you have to know is you're going to see this. I'm going to ask you, or Khan's going to ask you, or AP Test's going to ask you to just find the derivative. But there's a lot of different ways to ask that exact same thing. So they may say differentiate. They may say find the rate of change. Find the instantaneous rate of change. Find the slope of the tangent line to the curve. Find the velocity of a position function is really what that would be. So all of these things are just ways of asking for the derivative. And there's more than this too. There's also lots of different ways we would notate derivative. You got y prime, you got dy over dx, you got f prime x, you got d of f of x over dx, you got df dx. There's so many. Typically, it's these three that are most common that you'll see. Sometimes you see this. I've rarely seen this, but you just have to know that there is a lot of different ways of asking for the derivative. There's so many different words and so many different notations that I can throw at you, and they all just mean the same thing. They just mean find the derivative. Okay, and then here's our basic definition of derivative, or I guess you could say like the official definition. The only thing is that I typically don't use the delta x symbol or the change in x. Instead, I like to use this definition. The limit as h approaches 0, it's easier to write. It's easier to tell the difference between delta x and x if you use an h instead. So it would look like this. I guess I should say the derivative of x, or f prime of x, equals the limit as h approaches 0 of x plus h minus f of x over just h. This is the one that I actually use most frequently, and you'll see it. I think this is the one that is used most frequently, and the only reason is they just replace an h instead of a delta x. It just makes your whole writing a lot simpler because you're using a whole different variable instead of the same variable with a symbol in front. So, okay. That was a lot of explanation about the derivative. Let's actually talk about what it means. So, you got this graph here. And you have this point x, and you have some other point called x plus delta x, or this could be an h as well. But you have some difference of points. And if we were to evaluate the heights, right, that would be f of x. My lines may not be totally straight here, and that would be f of x plus delta x. The point is that, well, we could find a line between these 2 points, right? And it would be really close to the tangent. But what if this point moved closer and closer and closer and closer to the point so that it was actually right next to x? Or what if it was actually at x? So we're really saying, what if this thing, this delta x or this h value, approached 0? Well, you would see this point move closer and closer and closer till it was right on it. Could we evaluate that? Well, we couldn't do it before, but now that we have limit definitions, we can. And so that's what's happening here. We have the slope between these 2 points, right? So we have, this is like our y2 minus our y1. And then we would just have over delta x, because this is really like saying x plus delta x minus x. So this is really just the definition of slope. But what happens as we get so infinitely close to each other that we're actually right on top, that this thing becomes 0? We wouldn't be able to evaluate that before because you would just be dividing by 0, which we cannot do. But now that we have the limit definition, we can actually do that. We can find out what it would be. And so we're going to do that with this function. Here's the definition here. Let's work it out. This function is just x squared. And so I could plug in, instead of x squared, I'm going to plug in x plus delta x squared. So it's going to look like this. The limit as delta x approaches 0 of x plus delta x squared minus an x squared all over delta x. Okay, well, I can expand that. Hopefully you see what I did. All I did is just, my function is just x squared, so instead of plugging in x, I plug in x plus delta x, and here I just plug in an x, and here's a delta x. So now I'm just going to simplify this. So don't forget my limit notation, because that defines what I'm doing. What is x plus delta x squared? Well, that's just a perfect square expansion, so that looks like x squared plus 2x delta x plus delta x squared. And then remember, I have this minus x squared here all over delta x. Well, look, x squared minus x squared, that cancels out. And so what I really have is the limit as delta x approaches 0. And what I'm going to do now is I'm going to see if I can factor out a delta x from each thing. So I put a delta x in front. That would leave me with a 2x plus a delta x all over delta x. So these guys cancel. And so I'm really just asking for the limit as delta x approaches 0 of 2x plus delta x. Well, now that I've gotten this all simplified, which we've done this stuff before, we've done this type of problem before, now that I've got this all simplified, I can evaluate this limit. Well, this is just 2x. And so now I know that the derivative of x squared is 2x. And so that's how I got that function on the previous page. So that means literally anywhere on this graph, I could just plug in the x value on this graph into this equation and it would give me the slope. It's pretty neat. It's a pretty powerful tool. You can find the slope instantaneously of any point. So we'll talk more about that on the next video, but I hope that's making a little bit of sense, or at least making a dent in your brain for now. We'll talk more about it later. See you guys on the next video.